We will do 2 or 3 examples to better understand the failure theories for ductile materials. So let's start with example number 1. I'm going to heavily use my MATLAB code and show you how it actually works in detail. Okay, let's consider the case of a hot rolled steel. This steel has a yield in tensile and compression of 100 ksi. Give me a sec. And compression of 100 ksi. That's given in the problem. And from tables itself, your E for this particular material is 40,000 ksi. Okay, so that's known for the material that we are using. And one key factor, and it's important, it says that your true fracture toughness in 2 inches is equal to 0.55. So this value is bigger than 0.0, is bigger than 0.05. So that means we are already in the plastic region. Since we are in the plastic region, the material is ductile. Okay, since the material is ductile, it's a ductile material, then the theories that we have to use are regarding those, is regarding the ductile materials. Now, let's work with 4 different case scenarios, and let's see what's the factor safety for each one of them. Okay, so first, state of stress is actually equal to 70, 70, and everything else is 0. So when you look at the problem itself, if you realize, just as a nice review, this is already a diagonal matrix. So therefore, it's a principal state of stress, and it's a plane stress as well. Because it's a plane stress, I know that one of my stresses will be 0. So to start the problem, I need to know immediately when I do the problem, I need to know, first of all, do I have a design factor? The problem doesn't give me one, so let's just assume the design factor is equal to 1. If the design factor was not equal to 1, in this particular case, so assuming this is 1.15. Typically, if it's not given, this is the value that you should take. So then your real sigma xx will be 70 times 1.15. You multiply the stresses, each one of the values of the stresses, by 70 times 1.15. Okay, that's what you would do. But we are going to say this is not the case for my problem. We are not doing this, so we are just sticking with n equal to 1. Second thing you want to do in the problem is you want to make sure that you find your principal stresses, okay, and tau max. That just comes from your state of stress and your principal stresses, and you just need that information. Okay. Once you have that information, then we got 3 theories to work with. The first theory is the distortion energy theory that requires for me to find a sigma equivalent. The second theory is based on tau max, and the last theory is the Colomore theory. That theory doesn't have one of these quantities, but it says that all of this has to be your sigma 1 divided by yield in tensile minus sigma 3 divided by sigma yield in compression. Okay, that's the quantity I want to find, and I will compare with my values. Okay, so to start the problem, let's consider, let's find, let's solve the problem using my MATLAB code. Okay, this is the MATLAB code. You go to the failure theory and you press run. Okay, so now the problem is asking, when I press run, the problem down here is asking what unit. I'm working in inches, working in KSI. And as I told you, in this problem, it's actually equal to 1 because it doesn't specify anything, but typically 1 over 1.15. Okay? And what do I have? I have stresses. Okay, so I press number 2. Now, what you have to be careful here, I put 70 here, I have to put 0 there. Why? Because remember, just remember that your sigma xx is equal to the axial stress plus your bending stress. And since the whole thing is equal to 70, I assign the 70 to either one of these values. Okay, I cannot put 70 and 70, that will become 140. Okay, just keep that in your mind as you're doing these problems. Okay, then this is also 70, and everything else is 0. Okay, everything else is 0 in the problem because I don't have any shear. Are the stresses already applied? Let's assume everything is applied to the stresses that we have. So we continue. We want to do ductile material. Okay, this is 100, 100, and this is 40,000. Okay, and now the code is going to run, and it's going to give me plots. So then you have 2 files. The first file is failure theories. The failure theory file basically tells you all the inputs that you chose, okay? And then actually also gives you it gives you all the information that you need, that you actually gave. So now you're doing a ductile output file. They go to the ductile .txt, and here you repeat everything, and then it calculates your modular resilience. It tells you stress concentration in this problem are equal to 1. These are your state of stresses, and all of these points they'll given here. So okay, I was looking at a different file, so I just fixed it. So these are the state of stresses that are calculated. You can see my state of stress at the end of the day. And this is actually what we would have expected in the first place, right? So it calculates the roots for you, and it shows your roots are 70 and 70 and 0, which is expected, is a principal state of stress. So therefore, your tau maximum is S1 minus S3. And that will give you 35. Divided by 2 gives you 35. Then you go to your principal stresses, and these are just to calculate the plotting, this for plotting purposes. Now, couple of checks you have to do. The first check, you have to do the compressive and tensile checks. And those checks basically tell me, calculate the factor of safety to make sure that sigma yield in tension is equal to sigma 1 in tension, but this is in tension, okay? So this gives me 100, this gives me 70 from the problem, and I find that's equal to 1.429. And then you also want to check everything from the get-go for your compressive. That would be 3. the compressive value, typically you just put minus 100, that because it's compressive. And then S sigma 3 in my problem was 0, so I put a 0 there. And anything over 0 is infinite, so it gives you infinite. So you can immediately see that these are bigger than 1, so my structure is safe. So now we move to the next part, okay? So we have to do this check first. The second check now we do is for distortional energy. Okay, and the distortion energy says that sigma equivalent is equal to nothing else than uh, uh, sigma 1 minus sigma, actually, sorry, is equal to S1, oh, come on, sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus 2 times sigma 1 sigma 2 minus 2 times sigma 1 times sigma 3 minus 2 times sigma 2 sigma 3. And you take the square root of all of this. We already found our stresses, right? So after I evaluate the whole thing, I find this is equal to 70. Okay, so your margin, then from here, your factor of safety will be nothing else than sigma yield in tension, tensile. Remember, a distortion energy based on tensile theory. That's why I use tensile. Okay, sigma equivalent. So that gives me 100 divided by 70, and I get 1.429. So this is bigger than 1. We are safe. Second, sorry. The third case that we want to do is the case of tau max. Okay, so I find tau max, the maximum shear stress theory tells you this is absolute value of sigma 1 minus sigma 3 divided by 2. I plug in the values, I find the value of 35 KSI. So now I need to find my shear yield shear stress. I got two ways to do the problem. First one is assume this is half of sigma yield, or assume that this is actually square root sigma yield divided by square root of 3. Okay, so if I did this one, okay, I find that my factor of safety is equal to sigma yield in shear divided by my tau max, and that gives me 50 divided by 35, and that would give me 429. If I use this, I find a factor of safety is equal to sigma yield in shear and tau maximum. That would give me a value of 57.735 divided by 35, and that gives me 1.65. And you can see that typically we like to just use, so it depends on the programs that you work on, right? So we can use a lower margin and use this one. However, this seems to be very, very good with the test data. And this is what we like to use because remember, the smaller uh, the factor of safety, the bulkier I have to make my structure. Okay, so this bigger this factor of safety means that I have a little more cushion to bring my structure thinner. Okay, so and the last theory then is uh, the last theory is the column Moore theory, and that theory basically says that your factor of safety is going to equal to 1 over sigma 1 over S tensile minus sigma 3 over sigma S compressive. And if I replace all the numbers here, I directly find this equal 1.29. So we can look what actually MATLAB code actually does this for you. It calculates and tells you all the three checks, right? It does the tensile compressive checks at the beginning. It says it's infinite. And then it goes and does the distortion energy for you and tells you safe. It comes and does the maximum shear stress criterion and gives you the equation and actually does it for you. And then does sigma 3 for column more, gives you margin of safety. At the end of the day, it summarizes everything in a nice table. You may want to go here, and sometimes you have to open the folder where this is located at, and you can just open this file. If it doesn't open here, just find the folder. And then what you can see in this problem is, if we actually plot this, this is your loading line, and it's saying that your load line is actually basically along the horizontal, and and you can see the design point is located right here, so we are safe. Is within our boundaries. You can see that that all the other theories that we use, they all coalesce here because we are assuming the same sigma tensile in compression and in tension and compression are the same. Okay, you have to close this. Make sure you always close this before you run the file again, your code again, otherwise it's going to give you errors. Okay, so that concludes the first one. So now we want to go, let's do this problem. Your state of stress is equal to 0, 0, is 45, is symmetric, 45, 0, 0, 0, 0, 0. Okay, so again, remember the first thing, you make sure why we are using this equal to 1, and then find my sigma 1, sigma 2, sigma 3, and my tau max, and then I just work with the theories. So I'm just going to run the whole code using I'm going to finish the problem using my MATLAB code, and so go here, and I run the code. It's inches. This is 1. This is stresses. Axial value, I don't have axial values. I only have shear. So again, I can place my shear value wherever I want to. I'm going to place it here. It really doesn't do anything. But make sure the next one is 0. Okay. Yes, it is applied. I am working with ductile material, and this is 100, 100, and 40,000, and the code is going to run. Now the code is done running. Go to Ductile, and when you run the code, you can see this is my new state of stress. These are my principal stresses in my problem. This is maximum shear. So this is just to calculate do your drawings. Your first check, always make sure this is safe. Okay, and you can see that indeed it is safe. Okay, so we can continue. We can continue here, and then this is my von Mises stress using this equation. Plug all the numbers in here, and you can see my margin of safety is 1.28, 28, so it's safe. And using this equation, it shows you that we are indeed is 45 and we are indeed safe. Doesn't matter which criteria you use, both of them give you safe. And then you come here, you smaller a column more equation, and that gives you 1.11. So this is a summary of my uh, margins of safety for this problem. Again, if you want to check what your plot looks like, you can see that here in this problem is this is more of a shearing. So it tells you this is a case of anytime you are in this line, this says that you're pure shear or you're most likely failing due to shear. And it's consistent with the state of stress. We saw that in the state of stress. Okay. Okay, so I can run my second case. I can run this case again. This is inches, psi. This is going to be 1. Choices is stresses. Axial value minus 40. The other one I put 0. Minus 60. 0. And one of them I put 15. The other one I put 0. And rest of the values are 0. Yes, it is ductile material. And this is 100, 40,000, and it's going to run. And if I just look at my plot, you can see that the plot says that actually you are on this line when you're in this particular problem, and you're still safe because you're inside. So when you look at your file, this is your state of stress. We expected that. You can see that's what the state of stress we were asking for. These are your principal stresses. Everything is negative. That's what we expect to be here in the negative realm, in spot. So we do all the checks, and you can see that the compressive checks, these checks is infinite. This one is 1.1. And then if you summarize all of these, you can see that these are indeed your principal, these are your stresses. One thing I want to point out is, and you should know, that anytime you use sigma ys by dividing this by square root of 3, these two should give you the same answer. Okay, these two, if sigma yield in tension and compression are the same, these two must give you the same answer as well. Okay, yeah, one more case to run, and this case is very interesting because says sigma 1, sigma 2, sigma 3, this is a principal state of stress. Okay, so when I run my code, when you run the code, you find this is 2, 1, only stresses. Axial is 30. Make sure you don't double it. 30, and everything else is 0. Don't go too fast. Okay. 1. So use the ductile material. It was 100, 100. It was 40,000, and it's running. And let's see what the plot looks like. And you can see the plot is actually along this line, so that means it's a tension. Okay, so if it's going to fail, it's most likely going to fail due to tension. This is a tension failure. This line is shear failure. So when you have the problem, well, you can see that you can run this code again, and you can show that these are all infinite. So therefore, your problem is safe. So this concludes example number 1.